Day 8. What do we have here? Handheld halting. A lot of alliteration this year. Your flight to the major airline hub reaches cruising altitude without incident, while you consider checking the in-flight menu for one of those drinks. They come with a little umbrella. You are interrupted by the kid sitting next to you. He's got a handheld game console and it won't turn on. I want you to take a look. You narrow the problem down to a strange infinite loop in the boot code, your puzzle input of the device. You should be able to fix it, but first you need to be able to run the code in isolation. The boot code is represented as a text file with one instruction per line of text. Each instruction consists of an operation. These are the list of operations and an argument. This one increases or decreases a single global value called the accumulator by the value given in the argument. For example, this plus 7 would increase the accumulator by 7. Starts at 0. After this instruction, it immediately, the one below it is executed next. Jumps to a new instruction relative to itself. The next instruction to execute is found using the argument as an offset from the jump instruction. So jump plus 2 would be it would just skip the next one. Jump plus 1 is just the next one immediately below it. Jump minus 20 goes previously. And then no op is no operation. It does nothing. The instruction immediately below it is executed next. For example, consider the following program. This one would do nothing. So it would go here. And I think we have to, just the syntax of this, we're giving, it has to have a value to it. So this would add 1 to the accumulator. This would jump plus 4. So 1, 2, 3, 4. This would increase the accumulator. Minus 4. 1, 2, 3, 4. Plus 3. Jump minus 3. 1, 2, 3. Add 1. So this does run in an infinite loop here. First the no op does nothing, then the accumulator is increased from 0 to 1. This is an infinite loop. With this sequence of jumps, the program will run forever. The moment the program tries to run any instruction a second time, you know it will never terminate. Immediately before the program would run an instruction a second time, the value in the accumulator is 5. Run your copy of the boot code immediately before the instruction is executed a second time. What value is in the accumulator? So I think what we need to do is keep track of the instructions that we've done so far, and then every new instruction we check if it's in that set. And we can give these instructions a unique line of code here. So this would be 1, 2, 3. And then we want to keep the state of the accumulator during that time. So I'm going to do my usual thing of copying this input. This should be pretty easy to parse. There's just 4 instructions and the syntax is pretty similar. This is just an integer value for the instruction consists of the operation and then the input. And so that should be pretty easy to parse out. So we'll have a class that represents the input that we can use to parse through these instructions, and then we want to have some kind of executor class that keeps track of the current pointer and then returns the value of the accumulator when we run into a duplicate instruction. I think that'll work. Pretty straightforward. We're going to make a day 8. Day8.txt. I'm going to paste in this input. I'm going to make a test class. I'm just gonna, I don't know the naming of my classes yet, so I'm just gonna call this day 8 test. And I'm going to first parse this input into a set of instructions. IntelliJ is kind of running slow. I think for some reason my computer's running a little. I mean, I'm recording right now, so that's taking up some system resources, but it seems to be running a little bit slow today. But let's see what else I got going on here. I can kill Slack. Don't need this. Don't need Zoom. Okay. And I'm just going to call this parse instructions. And then we're going to, I feel like I should maybe create a test util class. Oops. And I'm actually going to make this an object because it doesn't really need state. And then I think I'm going to factor this part of it. I seem to be doing this a lot. Get resource as stream. The thing is, I need to pass in the class here, right? But, I want to just read these lines. I'm just going to do fun, read lines, and then this is going to return a list of string, and we want to, so I'll paste this. This is going to be this, we need to pass in the file name, which is a string, and then we also need to give it a context of this class, and that's going to be I think this will just be a class. Class of any, doesn't really matter. And then this needs to read lines. And I think this, is this a K class? Can I do that? K class, and then it's going to be .java.get resource as stream. And then that way we can just pass in this class for our input for that. So now I can just do, and I think what I'm going to do, I can static import this, that's fine. And then we're gonna do day8.txt. It doesn't like this for some reason. Can I just do out any? Okay, there we go. Test util.read lines, that'll give us all the lines, and then we want to create we need to create a class for instruction, and I also want to create, for the sake of cleanliness, I want to have an enum class for all of these instruction types. So I'm going to create a package for my day8. I'll create this enum, And then operation. The enum is going to be operation. Yeah. And then this will be no-op, ACC, JMP, or was that it? Was there just 3? Okay, yeah, there were just 3. Okay. I know, it's lowercase, whatever. And then I'm going to create a class for instruction. This is going to be a data class because it doesn't really, it's just basically a record. And then this is going to be a val operation. It's going to be an operation, and then val input, which is the int. So then we're going to take this, and then parse it into a list of instructions. And I think what I'll do is I'm going to create a separate function for just a private function just to parse these instructions. I'm going to give it a file name, it's a string, and then this will do this aspect of it. File name, and then what this will do is return a list of instructions. And then I'm gonna map this, and we want to split this with a space. So we're gonna do it.split based on a space here. Going to save this to a val, and then I'm going to create a new instruction of the split of 0, and then I'm going to do an operation value of, and I'm going to pass in this string here, and then I also need to convert this to an int, the second part. And I think this should work. I haven't actually tried parsing an int that has a plus sign in front of it. I assume that'll work. So let's try. I'm just going to try setting a breakpoint here. And I need to return this so that this stops complaining. So I'm going to say val instructions equals parse instructions, and then I'll pass in this day8.txt. And I'm going to print ln, just foo, it doesn't matter. I just want to see this breakpoint, I want to see how this behaves, and I also want to make sure that this can convert to an int correctly. Didn't like it. Okay. Oh, I see. I need to actually put this in a folder for day 8. So it's able to resolve those resources correctly. Okay, so I'm curious to see how this behaves. I'm just going to eval this real quick. So this should give me back 0, right? Yeah. And then the next one is +1. I'm just going to make sure that it gives me 1. Okay, that's what we expect. And then what about this? If there's a negative. Okay, so that gives me this negative int value. Okay, that's good. And then let's just take a look at these instructions it gave us. There were 9. Looks like 3, 6, 9. That's what we expect. Input 0. We have a no-op. Accumulate 1. Jump 4. This looks good. It's behaving as we expect. Okay, so now we actually need to handle these instructions. So I'm going to do a I'm I'm going to just create an instruction executor class. And that will keep track of this accumulator value, and it'll also keep track of the lines of code that it's executed so far. And it'll take a list of instructions as input. Call it instruction executor. It's going to have a private val. Instructions. And then that's going to be this list of instruction. And then it's going to create a val visited is a mutable set of this of int for the lines of code that it's been to, and then we'll have that just be 0 indexed. And then each time it will jump. And then this also needs to have some kind of instruction pointer so it knows the current instruction that it's on. And then it obviously starts at 0, right? And then I'm going to expose a function called execute until halt. And then this is going to return an int for the accumulator. We may even not need to do that because we could just I'm thinking of maybe having the accumulator be a method on that we could call on this class. So you could call this method execute until halt and then ask this class what the value of the accumulator is. I don't know, I'm ambivalent. I think I'll just expose it though because it needs to be exposed anyway. This var for the instruction pointer is private. We don't want to expose that. I think I'm also going to make the accumulator private, but I want the getter for it to be public. So I think I'm going to expose, Kotlin allows you to do this. I can have a private var and then underscore accumulator. Accumulator. I'm going to just call it ACC equals 0 because that's what they told us to start off with. I am going to rename it accumulator just to accumulator. And then I'm going to make a public val. And then it's going to have this getter on it. And that's going to be accumulator. So that way we can expose this. There we go. It's going to be an int. Doesn't seem to like this. Oh, this is going to be accumulator without the underscore. There we go. So this just exposes a getter on this private property that we can make mutable, and then this will just let us get that value. So now we just need to execute until this program halts, and a halting situation is that something in this set we run into again. So let's start off with let's do a while, and then while I think our conditions for running, are we guaranteed to have a loop? I think we can probably safely assume that we have a loop. I was thinking of what are the conditions at which we would exit the program, and that would be if if we ran the whole thing, right, and so that would mean the instruction pointer was greater than the size of the list of instructions. We could have that. We could say finished executing, and that's going to be a Boolean, and that'll return. That'll be return instruction pointer is greater than the instructions.size. And that's going to be -1 because we're going to have this be 0 indexed. The instruction pointer is greater than that, or the instruction pointer we've already visited it. So the instruction pointer is in this visited. I think in is the right way to do that. And we could also do contains, which it looks like under the covers this is calling contains. Yeah, okay. This is essentially calling this set contains this instruction pointer. So while we are not finished executing, we don't really care about no ops, but we do need to fetch the current instruction. So we're gonna go. This visited also doesn't need to. We don't need to expose this. We're gonna make that private. So I'm gonna just write some comments here to scaffold this code. We want to fetch the current instruction. We want to put it in map of visited. We want to execute instruction, and that would mean in the case of a jump, we would increment the instruction pointer, or in the case of an ACC, we would add that to the accumulator. So that's pretty straightforward. So a lot of this is just like fetching and adding here. So the current instruction is going to be instructions at instruction pointer. And then visited.add we want to add the current instruction pointer, right? Because it's just the integer. And then we want to execute. So for a no-op, there's a couple different cases where we're going to increment the instruction pointer. We want to execute the instruction, and then during execution we have to remember to increment the instruction pointer by 1. So let's say it's here. Okay. So we're going to do a when, which is basically a switch statement in Kotlin, and we're going to go instruction.operation, and then for no op, that's going to be really easy. And I'm just going to static import this just to be cleaner. All we're going to do in this case is increment the instruction pointer. We don't care what the value is. For ACC, we're going to do two things. We're going to increment the accumulator based on what the value is. So this accumulator is going to be plus equals this instruction dot input, and then we're also going to increment the instruction pointer plus 1, and then the last one is the jump. And all of that is going to do is instruction pointer plus equals that whatever the input is for that instruction. Okay. So let's run through this. Let's this function can be private too. Okay. Execute example input. So first we're going to go val instructions is equal to, I'm going to look at my local history here so I can just grab out what that was. I mean, I'm just trying to like resurrect that line that I just deleted, but whatever. I can just do parse instructions and then pass in this day8.txt. And then I'm going to do my val executor. It's going to be this instruction executor. And then I'll pass in those instructions. And then executor dot execute until halt. And then we want to get the value of the accumulator, and that should be, they're telling us that it should be 5, right? The value of the accumulator. So this is immediately before the program would run an instruction a second time, which I think we're handling this case in this executor. The while loop gets evaluated at the very end, right? So this instruction pointer will get, when it loops, the condition for a loop is the instruction pointer is set to a value that we have already visited. And when this while loop evaluates, it's going to say, is this instruction pointer in visited? So that would be immediately before it runs the second time. It'll bail out of this loop. And so we can safely, that behavior is something that we're already consistent with. Okay, so I'm just going to do this, and I'm also going to step through this just to make sure that I just want to watch this work and make sure that it's behaving the way that that we expect. And so it's showing us like, here's the order of the instructions being visited. Oh, I see. It's we renamed the function. Okay, so initially, this instruction that we're expecting is this no op with input 0. Okay, that's cool. Then have we visited? We visited 1. Okay, instruction pointer is 1. The current instruction, I'm actually going to set it here just so I can see what the current instruction is. Current instruction is going to be this ACC with 1, that's correct. After this loop, we want the ACC to be 1, yep. And then the instruction pointer is 2, yep. So that points to this one. And then this is 0 indexed. They're doing a 1 indexed, but whatever. Or no, this is actually like the order that they've been executing in, so that's fine. Jump input 4. So after this we want the instruction pointer to be 6. It is. And then our visited is 3, so we've gone 0, 1, 2. So we did these first 3, and then it does that, and then we've gone to 6. Instruction pointer is 7, which that was after this jump. 4, 1, 2, 3, 4. Yep. ACC is 2. Because that's right, so it's incremented this one time, and then it's another here. And the accumulator is 5. Perfect. Okay. I think we did it. I think that's it. So now let's get the puzzle input. save it as day8 full.txt. All of these. And then full input. I'm going to delete this. Well, I'm just going to print ln this executor. And this is 1723 is how far this gets to, or the value of the accumulator. That's the right answer. Cool. Part 2. After some careful analysis, you believe that exactly one instruction is corrupted. Either a jump is supposed to be a no-op or a no-op is supposed to be a jump. No ACC instructions were harmed in the corruption of this boot code. The program is supposed to terminate after or by attempting to execute an instruction immediately after the last instruction in the file. By changing exactly one jump or no-op, you can repair the boot code and make it terminate correctly. For example, if you change the first instruction from no-op 0 to jump 0, it would create a single instruction infinite loop, never leaving that instruction. If you change almost any of the jump instructions, the program will still eventually find another jump instruction and loop forever. However, if you change the second to last instruction, the program terminates. The instructions are visited in this order. After the last instruction, the program terminates by attempting to run the instruction below the last instruction in the file. With this change, the accumulator contains the value 8. So we want to fix the program so it terminates correctly by changing exactly one jump to no-op or no-op to jump. What is the value in the accumulator after the program terminates? So really, the problem was, so I think we can seek out the problem where there's gonna be I think the problem line of code is going to be the one that causes it to jump back to that loop. And that, I think, is the one that we want to change. So what I might do is I might save the value of the previous instruction. Maybe instead of a set, I'm going to create a list in this executor, and then I can examine this line of code here. And then when it hits a loop, that's the point where I want to change it to a no-op versus a jump. So instead of a set here, I'm going to make this a list, or a mutable list of int. And then I'm going to copy this, and I'm going to make a date8 corrected.txt. And then we can basically parse that input the same way. And this execute until halt, we still handle this case where the instruction pointer has been incremented beyond the instructions.size. So we can still run that until halt. Like even with a valid program, it'll still execute the whole thing. So I think that's really all we need to do here. when it reaches that loop, we just need to look at this list of instructions that it ran across. And I think I should be able to take a peek into that with the debugger. So I need to just find that bad instruction. Here's the executor. Sure enough, yeah, I have this visited. So this is the order that things were done in. Nine more. 257. 257 seems to have been the problem line. What does that do? Well, that doesn't really... Oh, I see. Was it 258 that was the problem? So this jump minus 230 would put us back to 28. Is that correct? So, okay, yeah, so it did, yeah, so this instruction pointer got set back. So that was the problem. So I think if I change 258, I think if I change line 258 to a no-op, I think that might work. Let's try it on our test input. And I think for debugging purposes, I might have a like a loop detected variable. I'm going to make this null. I'm just setting it to null to make sure that that way I can confirm that it hasn't been initialized yet. Finished executing. And I'm going to initialize this to false. And then if this gets tripped, then we know there was a loop. And then I'll take this out after, but I want to make sure, yeah, I just want to make sure that like when we run it against our corrected input, that it didn't detect a loop when it halted. I'm going to copy this to day8 corrected.txt. Oh, okay. Day8 full. I do want a full dash corrected. So I'm going to have it, yeah, 2 of those. I do need to change that line 258 to a no-op. And then let's try this day8 corrected for the example. And this is the one where they changed this last jump -4 to a no-op. And they're telling us that we only need to change one input, no-op to jump, jump to no-op. And so that instruction was the problem, so I think we got it. So we're going to parse this. This is going to be day 8 corrected. And then the accumulator we're expecting to be 8. And I want to just make sure that it didn't detect a loop. So I'm running it in debug. Executor, loop detected is false. Okay, accumulator is 8. Perfect. That's good. That is good. And we're going to execute the full corrected input. Corrected. Day 8 full corrected. And we want to just print that out. And I want to set a breakpoint so that I can check if there has been a loop detected here. We want that to be false. So sure enough, executor loop detected is true. Shit. That's not what we want. We don't want it to have detected a loop. So did we fix the wrong line? Is that what happened? This instruction pointer is now 556. I wonder actually if we changed a no-op to a jump, if it would jump over that bad line, and maybe that's what we were supposed to do. So I almost wonder, like, this is kind of suspicious here, because right now there's a no-op plus 390. And that no-op plus 390 would jump way past all of this. So I wonder. This might be a case where we have to brute force this, where we just like go through and flip the no-ops to jumps. That would suck, but plus 508. Yeah, I mean, there's all kinds of values here that might trap us. Ugh. I mean, I'm just kind of flying blind here. Yeah, loop detected true. I think we might actually have to brute force this and run. Just like go through every no-op, flip that to a jump, and then check to see that that ran successfully. So this might actually be a lot harder than I thought. Because there's a lot of potential ways that you could get the program to run. Like there could be a lot of potential loops in the program. Okay, so I guess we have to find it. So we need to parse out the instructions, run through the list. Let's try it on this example input just to have a smaller problem set to work with. I'm going to write a test that just does find parse the instructions, and then we're just going to brute force this. We want to go through and like flip each no-op one at a time to a jump. And that's kind of what they're telling us here. If you change this to a jump 0, it would create this infinite loop. If you change almost any of the jump instructions, the program will still eventually find another jump instruction and loop forever. If you change the second to last one, the program terminates. So they're basically telling us, like, brute force this. So instructions, I think what I could do this is very brute forcey, but I'm going to make a for loop for instruction. I think I'm going to do for I, because I want the indices, dot indices, and then I can just flip that. I can convert it to a mutable list and just flip that value. And then I do want to make this a first class citizen. This loop detected. I'm going to do the same thing where I'm going to make this a private. And then I'm going to make a val loop detected equals this loop detected, this private value. And then this is going to just be a getter. Get equals this. Okay. And I think I'm going to make a private find terminable program, and then it's going to take a list of instructions. And then we're going to work on it this way, and then we can just return that whole thing. Find actually, I think this will, why don't I return an int? This will return an int. And this will be the line to change. And so this instructions, what I'm going to do is I'm going to run the program I'm going to run a different program for each no-op or jump instruction with this flipped. So it's going to run through, I'm going to run one program with this flip to jump. I'm going to run one program with this flip to no-op. I'm going to run one with this flip to no-op. See if it terminates. Make sure that, and I'm going to have to create a new executor every time because this, actually at this, I might be able to reuse it. I'm going to start this over at, whenever you call execute until halt. No, I do have to create a new executor every time because it depends on the instructions. But just to make this idempotent, I'm going to reset the accumulator. I'm going to say reset. I'm going to set the accumulator to 0 and then the instruction pointer to 0. So that way, whenever you call this, it's going to return, this will be idempotent. It'll return the same stuff every time. And then this loop detected is also going to be false. And then we also need to say the visited is a mutable list of, it's just an empty list. And this needs to be, can I just, is there a way to just empty it? Empty, remove all. I think I can just do that. Maybe not. I am just going to make this a var as well. Visited equals empty list of int. List of int. Then we can get rid of this type and then this type. Right? Okay. So we do a reset and then we execute it. Something, it doesn't like this. Visited.add. This is going to be a mutable list. Empty mutable? No, it's just mutable list of blank. Okay. Okay, so now what we want to do, this is going to be where we flip the instruction. First, we want to flip it if it's if instructions at I dot operation is equal to no op. We want to first, we're going to check if it's, we don't really care if it's an accumulated instruction. Instructions at I is a, if that is a ACC, or the operation, dot operation is ACC, then we just want to continue. We don't want to go further than this. And then we're going to say val new instructions is if this, and then else we know it's a, otherwise we know it's a jump, right? And I think I can just do this inline here. Continue. And then we're going to create an executor. First we want to, I'm going to make this a mutable list of instruction. Or I'm actually going to take instructions.to mutable list, and then I'm going to flip this to new instructions at I dot operation. I'm gonna create a new instruction. I'm using a data class, so I can make a copy, actually. So I'm going to make this equal to instructions at I dot copy, and then instead of the I'm going to set it to an operation of jump. So I'm flipping that. I'm flipping it from a jump to a no op. Otherwise, I'm going to set it to a no op. Okay, and then I need to execute it. Val executor is an instruction executor of these new instructions. And then if executor dot loop detected, yeah, if it didn't detect a loop, then we want to return the current line, which is I, right? Okay, I think that should work. So we're basically running through these. We're flipping the no-ops one at a time. We're flipping a no-op to a jump. Instructions is immutable, so we're making a copy. We're only flipping that one instruction, and then we're detecting if there's a loop, and if there's not, then we're returning this index. So let's see if it detects the correct line, which we want to be the second to last one. So we're saying that line to change should be, in this case, I think this is 8, right? 0, 1, 2, 3, 4, 5, 6, 7, line 7. I need to actually run the return expression is required. Not found. So we're expecting that this is going to return. Okay. Find terminable program. Line to change is 196. Oh, I'm actually I actually ran it on my full input. Okay, that's promising at least. We just want to run on regular day 8. Oh, okay, so it did, it didn't actually debug, but it worked. Okay, so what did we say on, I'm going to say test find terminal program, and then I'm going to actually find one. And then we're going to go on day 8 full, and then we'll print that line to change. I think it was 196, but I'm just going to do this. Yeah, 196. So since it's 0 indexed, that's going to be 197. So let's check that out. Day 8 full corrected. I don't remember if I corrected this back, so I'm just going to copy the day 8 full, and then we want to go to 197. That jump minus 12. We actually want to make this a no-op so that continues here. So let's try this again. See if that worked. Execute full input. And then this should, we're expecting that this is not going to have, or actually we want to execute full corrected input, and then we're expecting that the loop detected is going to be false. Corrected full input, day 8 full dash corrected, and then yeah, we want I'm going to make this assertion here. Executor dot loop detected should be false, and if so, then print this accumulator. Let's run that. Sweet, it ran. So that's going to be 846. Hell yeah, we did it. That was fun. That was a good one. And I did it in just under an hour. Perfect. All right. Yeah, thanks for watching. That was Advent of Code Day 8. I'll see you next time.